Hi, everyone. Welcome to today's presentation in the Water Resource Institute's Water Connects Fall Summer Seminar Series. During the seminar series, we have focused on flood-related research by UVM faculty and flood experiences in communities. My name is Leslie Spencer. I'm a food systems PhD candidate here at UVM. And today I'm excited to introduce today's talk by my advisor, Stephanie Hurley, who's from CALS, and her talk is entitled Natural, Cultural, and Design Considerations for Resilient Green Stormwater Infrastructure. Stephanie's research and teaching span disciplines within the fields of landscape architecture, ecological design, restoration, and planning to facilitate healthy, sustainable societal and ecological interactions through design. Stephanie teaches landscape and ecological design courses that highlight principles, practices, and precedents, encouraging students to design projects that benefit both humans and natural systems. Her research on green stormwater infrastructure has led her to serve on advisory committees in Vermont, throughout the Northeast, Minnesota, and with the National Academies of Sciences. This talk will be about 30 minutes with 15 minutes of Q&A at the end. You can enter questions in the chat throughout or ask a question when Stephanie concludes. I will now pass it off to Stephanie.
Thanks, Leslie, and thank you for everyone coming out on this Monday after a long weekend. If you are just hopping online and you can mute your audio, that will be less disruptive for people. So thanks for the introduction, Leslie. Yeah, I don't need to say so much about myself, really, but I do have a kind of an intro slide on this. If I can get my slides going here. So, oops, just basically put some of my titles and affiliations on the screen for those of you who don't know me already. And as a general reminder, I'm coming from the perspective of landscape architecture and really thinking holistically about design for social and ecological systems. And so that has been a lens around a lot of the research I've done over time. So I suspect that this audience already knows the answer to this question, but I always like to include it just in case there's somebody who's like square one for stormwater runoff. Essentially, stormwater is rain that falls on impervious surfaces. We also call it runoff pretty synonymously, although stormwater tends to be used more in a development kind of urban context, and sometimes you see runoff more in like rural, agricultural, woodland contexts, but it's all stormwater. And it causes damage to water bodies and to communities as well. So the major ways we think about stormwater and its implications are in two categories. This first one is altered volumes and flows. It's basically water quantity, the amount of water coming down, hitting surfaces that are impervious. I've been using that word, but it's like hardscape, hard surfaces like rooftops and roads and parking lots, and unable to absorb into the landscape. And it increases the volume and the rate of flow over time, and can really be deleterious in our receiving waters, stream banks, lakes, estuaries, and so forth. The other kind of broad category of what stormwater problems are is water quality pollution. So above we have the quantity, and then we also have the quality. So there's not much clean water coming off of these surfaces, and it can be anything from soils and sediments to nutrients like phosphorus and nitrogen. I'll talk about phosphorus more than anything else today as a research specialty area. Heavy metals, bacteria, oils and greases, chlorides, road salt. And there's a whole host of new contaminants of emerging concern. They may be old contaminants, but the concerns are emerging in some cases that are flowing over the landscape in stormwater. Historically, we really have like societally thought of this as something to be conveyed away. The water falls from the sky and then is pretty much immediately contaminated on the ground, and you want to move it offsite as soon as possible. But if we flip our mindset, we can really think of stormwater as a resource as well. Traditionally, stormwater has been managed in the more urban settings that have subsurface pipe systems, as opposed to more rural settings where we see things like ditches and culverts. But in the more urban circumstances, some type of separated or combined system is typically used. And just as a very brief overview on that, with a separated municipal storm sewer system, MS4, That's actually a permitting designation. So some areas are actually permitted as MS4s. So the pipes with stormwater and the pipes with sanitary sewage from households and buildings and so forth are separately plumbed. They go to two different places. The sewage goes to a wastewater treatment plant, and the stormwater may be not treated at all. It may just go into inlets in the road, through pipe system, and into a downstream receiving water. In a combined system, the pipes are shared. So in some cases, that means the stormwater is treated because it goes with the sanitary sewage to a treatment plant. However, in storms of various sizes, sometimes not even that large a storm, this combined flow can exceed the capacity of the wastewater treatment plant, and then you get a discharge labeled an overflow in the diagram. In that case, you get a combination of sanitary and stormwater going into the receiving water is completely untreated. So there's problems with both scenarios. So when we think about development, we can really compare what the natural landscape would have looked like hydrologically, as well as in terms of natural capacity of soils and plants to provide filtration. And that's in this nice diagram I borrowed here. But I'm also really interested in taking these built environments, the developed land, and engineering them to behave more like the natural systems. And that, generally speaking, is taking an approach we refer to as green stormwater infrastructure, GSI, I will say for short. So green stormwater infrastructure is GSI. And so we really want to like have a mindset of what does a natural system, nature-based solutions do, and then apply those things in the built environment. So expanding on the definition of green stormwater infrastructure, uh, it provides both the water quantity, the storage of water, as well as water quality improvement. And through these main sort of verbs in the next few bullet points, we focus on reducing the amount of impervious surface and increasing vegetation cover. We slow the rate of stormwater flow, allowing for evapotranspiration. We infiltrate rainfall to reduce the amount that's running off, and it also has a benefit for recharge and groundwater recharge for drinking water and stabilization of base flow in streams. And we use soils and vegetation and take their natural capacity to filter and remove and capture pollutants. You see GSI typically in more new developments, it might be required, but you can also retrofit existing sites. And historically, we have associated the emergence of GSI with urbanization and urban landscapes in developed areas. But more and more, it's being applied in more rural settings. And I have an example coming up of an agricultural site that uses these same principles. So it might even just be a small village as opposed to a large city where some of these same ideas can be implemented. It can be an aesthetic amenity, and as someone with the landscape architecture and design background, I want that to be an aesthetic thing to have green infrastructure in the landscape. It also can provide habitat for people and other species, so really a lot of placemaking and sort of visual appeal, but also wildlife habitat, bird habitat, pollinator species. It also collectively can mitigate urban heat islands and impact climate change. There's some examples on the screen of different types of green stormwater infrastructure. This is not, I have a longer list later, let's just say, but here are 6 types that are pretty common. And I'll kind of, I think you can see my mouse. So starting in the center, these are porous pavers and pavements. They appear like the hardscape we're familiar with, but they let the water sink through and are stored in subsurfaces underneath. On the lower left, there's a couple examples of green roofs. In the center, at the bottom, a couple examples of bioretention rain gardens. To the lower right is a constructed stormwater wetland designed specifically not for other wonderful things about wetlands, but specifically to hold stormwater. A large detention pond in the lower right corner. And then this pear in the upper right corner is basically it looks like a common street tree, but there's a lot more going on underground where there's a massive storage infrastructure provided to hold that water. And it also benefits trees because they need more space in urban environments for their roots. So that's sometimes called street tree pits. There's a lot of proprietary names for all of these. There's lots of companies that make special pavers and special types of tree pits. So I'm trying to use the more generic names here. Collectively, there's a lot of opportunity for green infrastructure to build resiliency. And green stormwater infrastructure, I would emphasize, is a subset of the bigger green infrastructure, the converting of cities to focus on nature-based solutions. So, for example, in this image from EPA, it talks about green infrastructure like rain gardens and permeable pavements, managing flooding. In number 6 down at the bottom, we're looking at shorelines and buffers and storm surge. And this is obviously a coastal example, but this can work on large lakes as well, like Lake Champlain. So this kind of cartoon, I'm really wanting to see made a reality in sort of the real world. And forgive the pixelization of this image. It was just kind of the right topographic depiction for what I have in mind. So you see above is sort of a non-urbanized environment, and down below is more urbanized. And a lot of the conversation throughout this seminar series has rightfully so been very focused on these kind of low-level floodplain conditions. And you can see how our society has tended to put roads and rails and so forth right in the floodplain, very close to rivers, which may be meandering, they may be straightened by people. But I'm really interested in thinking kind of upstream and what can we do in these environments in the uphill areas to keep the water from flowing down. This EPA image promises that it can help manage flooding to use green infrastructure, but what scale of flood? And I'm sorry, I'm not going to fully answer that question today, but I want you to keep that idea in mind of like how much of this can we maximize on the landscape to actually have the upper watersheds soak up and sponge up the storms so that the impacts in the floodplain are lessened. So really thinking about siting green stormwater infrastructure to maximize landscape resiliency and really watershed resiliency. So along these lines, I have 3 kind of big questions. The first is what can we do at the site scale to incorporate GSI and improve its performance? And I have a bunch of research we've done in my lab group on that topic. What are we already doing? We've looked into this too, trying to get a lay of the land, especially in particular 2 studies from Vermont that I'll talk about today that are looking at what households as well as municipal officials in Vermont are doing already. And then that big picture thought of how much GSI do we need collectively to make an impact downstream? So how much could we have in our watershed to really make a downstream impact? So one of the 2 surveys that I am going to talk about today was actually conducted, I think, 7 years ago, 6 or 7 years ago, but was just published this fall after a lot of data analysis and a lot of working through our own timelines. But I'm really excited to report this. And we had at least 136 towns, 100% of the counties. And these are surveys of Vermont municipal officials, so people who are in towns and cities. Now, what we call a city in Vermont, I will remind you, when I showed this slide recently in a Washington, D.C. Conference audience, greater than 5,000 people equaling a city, I had to like make a big caveat. This is Vermont, what we call a city here. Obviously, these are the scale that we're using here for urban, mid, and rural. But even at this small population state, it really breaks down. And you can see in the respondents from this survey, the mid and urban-sized towns actually have town managers and implementers who are answering this survey because they have stormwater in their wheelhouse. This is something they work on as part of their job description. Some of the small towns in more rural settings, was the other about 43% of the rural respondents were town clerks, treasurers, and assistants. So they took the survey, but they're like, it's not their specialty to be working on stormwater or something else in public works. So we asked them sort of all this longer list of possible types of stormwater infrastructure, ranging from green to somewhat gray and traditional. What was already in effect in their towns? Is there at least one example of these? Sometimes there's many. And then what are they likely to implement in the near future? And so the 2 bars represent already existing, the blue, and the orange is likely to be implemented in the future. And so what we found kind of looking at this, when you arrange this kind of the least to the most implemented, it actually turned out that the more complicated types of GSI were less likely to be implemented, and that the places that were implementing them were more likely to be the large municipalities in Vermont, the bigger, medium, and quote, urban, the higher population areas. Often that means around Chittenden County, but it could have been something like Rutland or Montpelier or Barre. maybe I'm not telling you specific the answers in the survey, but it could be, something in southern Vermont too, like around Bennington. This sort of mid-range, lower tech GSI, I'm particularly interested in bioretention systems. We'll talk about in the next few slides. There's with the connection to the storm sewer and more piping and plumbing, we kind of labeled more of the high tech and the lower tech. Um, you'll see is like the basic rain garden. But there is some growing interest and likely to implement in the near future. And this was one of the only places where there was more interest in the near future than already existing, similar to the tree pit and the gravel bed wetlands since this time have skyrocketed. They've been a lot more put in around Vermont. And I do want to make the point that even using the same stormwater management manual, and Vermont is making, since I've lived in Vermont, the second round of revisions to our state stormwater management manual, it doesn't mean cookie cutter design. So people are using the guidance, but the designs look all different. And this is just an example from an interesting study of detention ponds in Chittenden County and their widest transect cross section and what those sort of look like in terms of depth and width and volume storage and then the size overall of the ponds with respect to each other. Their pollutant removal will vary as well as their size. So I'm showing this image. This is a bioretention system that I designed and worked collaboratively with others on. And this is down on the waterfront by Echo. It's the parking area for Echo. So the lake is sort of right here. And it's right on the lake shore, which is interesting because I've been talking about getting more into the upper watershed. But there are some limits on this site that were really challenging, like high groundwater. And we were still able to develop a design, moving the bioretention to be wider and flatter than it would traditionally be, that could have an increase in resilience for this site. So I get excited about bioretention because I feel like it exemplifies this idea of GSI, of using natural processes and specialized materials to address water quantity and water quality. And there's a lot of room as a designer to creatively implement this in the built environment. And it's also the most popular form of GSI so far, but questions persist. So leaving the sort of more designery site, this is the image of our now 12-year-old bioretention lab at UVM right outside Jeffords Hall. And the main categories of questions that all these PhD students have been working on over time. Myself as PI, I worked with 3 different now doctoral students on this lab site, also with some co-PIs, Carol Adair and Eric Roy. How can we optimize the soil media to achieve both hydraulic conductivity in order to manage those flows and volumes and plant growth because we want the aesthetics to work and we want good coverage and biodiversity. And then what are the benefits and impacts of the various bioretention media amendments? And that extends to this site as well as a couple other sites where we look at those benefits and impacts. I'm not going to expand for too long on the different studies we've done here in part because I've presented on these before in multiple venues. Happy to talk about them in the future. But we've looked at water quality as in sediments, nutrients, heavy metals, the effects of different proportionate amounts of rainfall, simulating what a storm might be like in a climate change future on the same site with one today. We also measured greenhouse gas flux. And we did a study of compost leaching, which was complementary to this. And so we really found one of the highlights that I have talked about before in many presentations, but I need to emphasize again, especially if you're new to this. When people think of bioretention rain gardens, they think garden, I want to grow a lot of plants and vegetation, so more compost has to be good, right? Well, I fell into that same trap myself. And in this project, so the figure here on the lower left is from the previous project site, one of the figures from one of those papers. We found both nitrogen and phosphorus in multiple forms was much higher leaving the system than going in. So there's runoff from the road. It goes in through these bioretention systems that we designed, and it picks up a bunch of nutrients before the effluent. So the subsequent lab study confirmed the issue is compost leaching phosphate and nitrate. And so even after 4 years, the compost wasn't flushing out. And so subsequently, the recommendations that came from this is we can design low P composts that are based on yard waste, leaf litter, and wood waste, minimizing any manures, biosolids, or food scraps in the compost feedstocks. Also, the compost is there to grow plants, and a lot of times bioretention is just designed in layers, and the plant roots can't even reach some of the compost. So really spot applying locally where the plant roots will grow and get started will give the plants a boost from those nutrients as well as the water holding capacity without causing problems related to leaching because the stormwater comes in and flushes through the soils without the plants ever having a chance to uptake those compost-derived nutrients. And then also we need to be really careful in nutrient impaired waters, anywhere prone to saturation. The longer a compost is wet, the more nutrients leach from it. So this and some other research that my colleague Eric Roy and others have done on gravel wetlands designed again for stormwater treatment has led us to develop a phosphorus testing guideline. So we have this is available on the Lake Champlain Sea Grant website, and we're hoping gets incorporated in the next round of the Vermont Stormwater Management Manual to really be able to know what to expect of the soil media when it's installed and avoid this risk of leaching the very nutrients like phosphorus that we are trying to avoid sending downstream. So here's another sort of soil study, and it relates to the previous slides because we used low phosphorus compost in on the far right in this section profile of the design of the study. The other question, so we have here the ability to compare with and without compost. How did the performance go? But I've been asked a lot over time as a designer, do we even really need plants? Can't we just put these big, gravel filters in the environment and soak up the water? And that probably does solve the water quantity side, but I would argue that the water quality side is really at risk there, but I didn't know. I didn't know for sure if how much are the plants doing for water quality versus a more ornamental or decorative role for the plant species. And so this research was actually conducted, it's one of the examples from a farm landscape, and two different master students worked on it. This photo shows about 4 months after we initially planted this project. And you can really tell with the water holding capacity and the nitrogen and the small amount of phosphorus, the same plant species, same number in both bioretention cells here was thriving more in the presence of the compost. And then, of course, we didn't have any vegetation here, so that looks as expected. But over time, over the next couple of growing seasons, they were equivalent in biomass and as well as very, very similar, not statistically different plant survival. So the switchgrass really grew up very successfully, even in the absence entirely of any compost, as well as in the low P compost environment. And this study that came out, I think 2022, looks at the influent here of total phosphorus and soluble reactive phosphorus, and then compares to those three different scenarios. And as a reminder, cell 3 has the compost, low phosphorus compost and vegetation. In the absence of vegetation, there were some statistical differences in performance that generally showed that cell 2 had the best water quality, where there was no compost at all, and there were plants as opposed to unvegetated. So this is I think Jill Sayers and many of you know from the Green Infrastructure Roundtable, this is part of her master's research. We've also looked at another kind of ingredient in green stormwater infrastructure that can help with the phosphorus problem. So this is drinking water treatment residuals. I don't care for acronyms that have the word W or the letter W because it takes a long time to say DWTR. But DWTR is drinking water treatment residuals, and they are an iron and aluminum based material, especially aluminum in the case of what we're studying, that is left over from the drinking water treatment plant process. So it's spent as far as it can be used for treating water that we're going to drink, but it's basically effectively an industrial waste product, and it's rich in aluminum, and it has some iron components that can help sorb the phosphate. So the positive cations connect to the phosphate, the anions, and we have studied it now in multiple lab studies, but this is one of them. It's a diagram here. So we looked at with no drinking water treatment residuals as a control, and then mixing them in just as a solid layer, because as I said before, a lot of bioretention designs just layer in the different materials like a layer cake. And then we also tried mixing the DWTR in with the sand. And generally speaking, we found that the performance was better from both hydraulic conductivity as well as phosphorus removal in the mixed layer because it allowed more contact with the water. And they're actually kind of like a slightly gelatinous material, like damaged gummy bears. And so you can imagine that the challenge of getting water to pass through them in a solid layer can create flow paths that are not making maximum contact between the water and also making the water move through and a clogging versus flying through back and forth as opposed to kind of a soaking in. So then we took this out to the field from the laboratory, and this was back on the first site that I mentioned, the bioretention lab. We dug up the soil media for 4 of the 8 bioretention cells, and we cleaned the liner to try to get all the old soil media out of there and all that compost that was probably still leaching 7 years later. We put in a new soil design and replanted it. And then Michael Immense study here. This is a nice image of how the monitoring setup went. So we are able to therefore compare in the field with and without the drinking water treatment residuals how the system functioned. So the center is the profile of those systems that I was just showing you. And on the right side here, you can see the influent versus effluent. And this is what we want. We want less nutrients, and this is cumulative P load in this figure. So less mass of phosphorus in the outflow than the inflow. In 2019, even with just sort of like a baseline of no GWTR, just the sand and the low phosphorus compost, we did have some capture of phosphorus, but by the next year, 2020, we're starting to kind of lose the edge compared to in the presence of drinking water treatment residuals, how well the outflow had the phosphorus removed. On the left, I know it doesn't look like a damaged gummy bear as I had potentially hinted earlier, but when you feel it, there's a lot of gelatinous materials there. But these are actually freeze-dried and prepped in the lab. These are all different DWTRs. They're alum-based or polyaluminum chloride. So I was talking about the alum content previously. And that was studied for a paper that's in prep from Marcos Cobau's thesis, looking in the lab at many different materials from around New England to see sort of, do we already have enough DWTR in our region to be able to effectively trap a lot of the phosphorus that we're putting down in the landscape. So the kind of outcomes of this study is that there are different chemical and physical attributes across all of these 12 that we studied here, or 11, plus there's 2 pictures of the same one. In general, if you're looking at a drinking water treatment residual, that's alumina-based. It should have low bulk density, high porosity, and high aluminum and iron oxides to predict absorption of P. We also were aware of some potential adverse impacts or risks. So we studied heavy metals, specifically arsenic and manganese. We also studied, but arsenic was the only one kind of even on our radar as possible risk. And then PFAS, which are ubiquitous. I'm not going to talk about them extensively here, but we also looked at PFAS in both the source water and in the residuals themselves, because obviously you don't want to put something out in the landscape and have it have a deleterious consequence or a perverse consequence from what you intended. And again, what I said before, mixing it into sand is more effective for both phosphorus removal and hydraulic conductivity. Brief side note, this is a sand filter study by Michaela Shimbura. She just graduated this year in 2024. We used DWTRs in a sand filter as well and had 2 different sand filters, in fact, had great results reducing the cumulative mass of phosphorus between the inflow and outflow for this study. So stormwater sand filters are less green than bioretention. They're not vegetated in any way, but they're still part of the overall puzzle, and they can be inserted subsurface. So you can really have a lot of activity on top of them in dense urban environments. This is another study I'm not going to get into too much, but last year I wanted to just share, we're still processing results from Sam Brewer's data. This is kind of a between lab and field scale mesocosm study. So looking at simulating different amounts of pollution in different rain events, and then going through different mixes of soil media and the same plants, but 3 different native plant species. So really fun study. This is the 4 different mixes that you can see here. across the top. So we included a low phosphorus topsoil. It's just labeled topsoil here, but was actually tested using the guidance to be determined as low phosphorus. We also looked at wood chips for denitrification and drinking water treatment residuals. And this table is some initial results from this research. I'm still kind of wondering how the sand performed almost as well as the DWTR. We did see quite a bit of flushing of phosphorus from some of the early storms from the wood chips. So there's more story coming in future presentations. So we know more about how different forms of GSI, especially bioretention, can function, and ways to improve GSI performance, especially for phosphorus removal. But how do we get more GSI in the ground? So back to talking to people. I mentioned a previous survey, and there's more on that one, but this is actually a household level survey that was published in 2018, where we talked to households all across Vermont about their interest in adoption of green stormwater infrastructure. And some of the things we asked about were whether they had any stormwater or flooding issues directly at their household on their own property. We also asked about whether they had observed issues with stormwater nearby in their same neighborhood, not necessarily at their own house, but a neighbor close by, walking the dog around the block. Have you seen stormwater issues? And then we also kind of compared that to the regulatory landscape. So towns that, this is looking at watershed scale, so towns that have those previously mentioned MS4 permits, the more urban areas in the state, as well as whether or not their nearest water body in their watershed was impaired being listed on the Clean Water Act 303D list. And so some of the findings from that study I just wanted to highlight today. There was a higher likelihood that people wanted to adopt green infrastructure if they had previously experienced on their own household or in their neighborhood problems. So statistically, much more likely if they had personally directly had an experience with a stormwater or flooding problem, their interest in adoption was increased. People were not at the household scale. Residents were generally not kind of aware of the regulatory policy impacts. There was a slightly, you can see from the figure that there was a higher interest in adoption intention there, but it wasn't statistically significant whether there was a regulatory context for their interest. With the exception that if they lived in an MS4 municipality, it did predict intention to adopt rain gardens. So that was like, again, this is bioretention in its more common name. Younger respondents also had more likely to report intention to adopt, and green behaviors emerge as something, green behaviors like that being green as a demonstration, and to demonstrate your commitment to the environment. It could relate to things like putting up solar panels or driving electric cars. In this case, even the willingness to divert roof runoff, which people didn't think would be that effective, were still expressed as something that people would want to do. So that also emerged from this research. Another figure from the same research that I think is important to consider. So many of the residents that were surveyed perceived that there was no need for the practices. And I'm really curious because of the connection between interest in adopting and direct experience with flooding, if those data would change since this was conducted in 2017. Would it be different in 2024 or 2025? People have now been experiencing more floods, and they've seen neighbors, and then they've helped neighbors who've experienced these deleterious effects from the built environment. So that might change the expression that maybe there's no need. Obviously, cost is a barrier in most of these cases, and subsidy programs are really important to address that. And then aesthetics, I'm glad to see from a design standpoint, wasn't really a big predictor of a big barrier to adoption. So aesthetics was not really an issue for people, but cost, no interest, no need, not suitable on my property, etc. So I just spoke about a survey of households, and this is back to that newly published survey of municipalities. So I talked earlier about sort of the urban to rural municipal officials in Vermont. Another aspect of that survey was looking at the aesthetic appeal and maintainability of different scenarios shown. So in this case, we have a very conventional sort of street inlet in example A. There's a compatible image above and a cross section below. So sort of the perspective view and the section view for all of these. Scenario B has just simple grass bioretention. Scenario C adds trees, and D is a mix of perennial vegetation species. I've shown this before, but I think it's really important for folks to be aware of, the visual appeal. So we have sort of the blue is the more appealing and the red is the less appealing. So there was high visual appeal for all the vegetated examples that you can see here, and particularly the grass. People really like grass and lawns. That's another study. Um, and then when you get to maintainability, you're seeing a lot more red show up on the screen. So this is a factor of who can actually take care of this GSI in our environment. And then I'm not going to go through this in detail, but you can get the general sense by the amount of red you see in each figure, where the work not being done at all, work being labeled not applicable to my town or city. Those red colors here are much more proportionately present in the rural survey responses than the urban. So in the urban areas, they're doing a lot of the maintenance things that need to be done to keep green infrastructure functioning. In the rural areas, they're not sure it needs to be done or they can't do it. So that's an area that could potentially be helped by more funding. Oh yeah, I can hear you on there, Janelle. Or yeah. Okay, so somebody talking over me. I'll try to keep going. Okay. Couple more slides. I know it was promised as 30 minutes, but I got confirmed I could speak for 45. So I think I'm on track to do that. So that same study really kind of statistically looked at what I just shared about the maintainability and visual appeal. And we found that the more urban municipalities in Vermont had higher diversity of GSI and were more ready to maintain green stormwater infrastructure. And this was based on population, the amount of development, and then EEPV is actually a substitute, as many of you in Vermont probably know, it's a substitute essentially for tax base. So the higher amount of these things was more likely to mean more GSI and more ability to maintain it. In this other part of the same figure, we looked at stormwater policies, stormwater plans, and other types of regulations. And so if a town already had existing stormwater policy in place, whether it was federal, state, or a local policy, a plan, including plans in development, which is interesting. If plans were in development, people were even more excited. And these are municipalities responding, the officials from the towns responding to this survey. People who are working on their plan were more excited to adopt GSI. And then it also indicated their perception that it could be maintained. So whereas the households were not influenced in the previous example by policy and regulations, the individual residents were like, oh yeah, I don't know, maybe the people from the municipalities were very affected by the presence of a policy or regulation. So that is a vehicle to get GSI adopted, is working through government. Zooming way out, and this is no longer Vermont, but I did want to just talk a little bit from a siting standpoint. If we think that we're struggling to cite GSI in our very green mountain state, there are ultra urban areas that are trying to do this as well. And this is the Charles River. You can see downtown Boston on the right, Boston, Somerville, and Cambridge, Massachusetts here. These are actually slides I'm sort of revisiting for my own dissertation, so they're quite old now, but there's more than one way to do this. So there's a more consolidated approach that's depicted in the image on the left, where maybe we don't have space because the buildings are quite dense, but can we find and purchase or get someone to donate a large area to create kind of a pond park system versus really distributed. Like this is an example of many bioretention or biofilters where they would be everywhere you turn. Every time you parked a car or came out of a building, they would just be kind of all over in the landscape. And so these images were actually used in a survey that Leslie, who kindly introduced me today, has been helping me kind of finalize the processing on. So we asked experts in a focus group a number of years ago, I think it was 2018, I should have that top of my head, maybe 19, about the implications from a planning standpoint of the more consolidated scenario, so on the left side here, versus the more dispersed scenario. And you didn't have to they could say yes to both. They could say both were great. They didn't have to compare them to each other, but these are the images they saw. And so red here is the consolidated range of responses, where 5 is the sort of best, most advantageous, and 0 is the least. And you can see that this group of experts from all over the Northeast really kind of mostly, for most criteria, agreed that you can make it work in a consolidated or dispersed approach. So maintenance would be kind of equally challenging for either one. Different types of levels of resilience. One of the ones that I think is interesting, resilience to whole system failure, has more strength in the dispersed category in terms of if the infrastructure from a single pond park blows out, there goes all your water. Whereas if it's dispersed throughout the landscape, there's lots of different places to add resilience to the system. But an interesting aspect, when we looked at the social and ecological considerations, the dispersed, more typical GSI that's close to where the rain falls and becomes runoff starts to take the lead. You see more of the blue bars moving to the right in the image. A couple exceptions are fish habitat would be more preferred in consolidated and less preferred in dispersed landscapes. But in terms of all these things like community amenity, we haven't gone deep enough in this research yet. And so the one last study I want to talk about is that in cities all over this country, there's inequity of distribution of GSI. So Amir Johnson just defended 2 weeks ago his master's thesis in agriculture, landscape, and environment in my department. And this is part of his literature review, looking obviously at much larger cities than we have in Vermont. But the general issue is that a lot of times underserved communities are the recipients of the urban heat islands, of the flood-prone areas, and really the sort of like historic segregation and redlining of neighborhoods and income disparity that often tracks with race has led to inequity of distribution of GSI in Philadelphia, in Baltimore, in Los Angeles, in Indianapolis. And some of this is explicitly GSI, and some is like street trees, which is a form of the broader green infrastructure, or green alleys, similarly. So I'm not going to repeat any at length Amir's thesis, and he actually looked at both Milwaukee and Washington, D.C. But just as an example, Washington, D.C., you can see the historic income and racial disparity. A is median household income, and B, the map on B, is Black population as a percent by census tract. And Washington, D.C. collects a lot of data on GSI. They catalog all these things you can see on the table on the right, and there's over 38,000 implementations of GSI. So Amir and I went through and looked at what sort of the lower investment forms of GSI are. Rain barrels, rainwater harvesting, and disconnection of a hardscape to a more pervious area. Some of the other things are more expensive and have the items in green as opposed to orange would have bigger impact on things like urban heat islands. So this is just a glimpse of one of the outcomes from this research. And what we found in Washington, D.C. actually was that there is an increase with Black population of green stormwater infrastructure. So that was different than those 4 other cities that we had talked about. There's more GSI quantity on the landscape as you go to the right across the x-axis toward the neighborhoods and census tracts that have the higher percent Black population. However, part of that is driven by an increase in proportionate low investment GSI. So a lot of what's there is, you can see from the writing on the right side here, 32% increase with each 10% increase in Black population in the low investment GSI is higher than the baseline 21% increase. So also, this is not featuring median household income on this figure, but the highest income areas were less likely to have any of the low investment GSI present. It was more likely to be each of these dots represents a GSI intervention at a specific census tract. I should have said that at the beginning to interpret this, but so each of these is a census tract, and how many GSI There's over 400 in many of these census tracts. You can see up here how many GSI implementations there are. Again, Washington, D.C. collects a lot of data and has done a lot on green infrastructure. Okay, so back to my original big questions before I go to your questions. What can we do at the site scale to incorporate GSI and improve its performance? This is my career in this paragraph. Design stormwater capture and filtration systems that are inspired by natural processes, sized to capture larger storms, and utilize soil media and vegetation that retain nutrients and other pollutants while improving aesthetics on site, recognizing maintenance needs in design, and distributing GSI in the landscape according to both biophysical and sociocultural criteria to enhance resilience of cities and towns. What are we doing already? We've made a lot of progress in Vermont and around the country, but more needs to be done, in particular to translate research to practice and set policies to mandate nature-based solutions. And as promised, I'm not fully answering this last question. How much GSI do we need in our watersheds to collectively make an impact downstream? I'd love to work on this with you, so let's team up. I see this as an opportunity for more design research, modeling, monitoring, altering policy, really thinking spatially about watersheds, and outreach and communication to spread the word about what works in green infrastructure, what could be done better. Voluntary as well as regulatory green infrastructure needs to be a part of the solution. So this is a very long slide with lots of different references, but at the bottom, they are all listed on Google Scholar. So if you look at Stephanie Hurley, Google Scholar, you'll see the full list of publications. And if you can't get to any, let me know. And I really want to thank all of these excellent people and funding sources for this body of work. And I'm happy to take questions. I don't know if I can see the chat.
I
Let's
can
see.
let you know if things pop in. Um, yeah, feel free to type them in or say them aloud. I can start us off with a question, Stephanie. Um, I was really interested in the study you talked about with the household survey. Did you say it was in 2018?
Sarah is on
2019.
the call, I think.
Oh,
I don't, actually, she
hi,
might not.
Sarah.
I don't
Um,
want to call her out. So my recollection is that since we published it in 2018, we did the data collection either 16 or 17. It was definitely post Irene significantly,
okay.
like or so. Mm-hmm.
Because my question is, you said that people with a personal experience with flooding were more likely to maybe adopt GSI at home. And I was curious, given, our back-to-back summers in Vermont, if you think people's perceptions and I guess willingness to adopt GSI on their property might be different now that we've had two incredibly, incredibly wet, flooded summers.
Yeah, I mean, I do think there's more interest. I think there needs to be more from a resource standpoint in terms of how you actually can build something that's larger and enough bang for your buck. But I also think advocating for our public spaces like schools and parks to include these types of infrastructure is really important. And people can do that even if even if they're not homeowners or they aren't, able to modify the landscape where they live. I think that's the big piece of it. I suspect that if we asked some of these same questions across Vermont, we would hear more people saying they're interested in adoption also because they've heard more about it in the intervening 6 to 8 years. Yeah, that's a good question.
Hi, Stephanie. I have a couple questions. Thanks for the presentation, by the way. It was very informative. But I work with Shelburne coordinating their stormwater challenges, and got a couple more specific questions. But kind of, I think one of the challenges we face with, sometimes we do have residents that are interested in doing like small scale green infrastructure on their property, but we're blessed with Lake Champlain clay that, has really low infiltration rates. And also sometimes we're in areas that have really high water tables and some developments that, back 30, 50 years ago were built in wetlands. So they have really high groundwater tables. So it's often hard to find green infrastructure solutions for those areas with really low infiltration rates and high groundwater tables, especially at that smaller scale when we're not looking at doing like a neighborhood um, gravel wetland or something. And I wonder if you could talk to that and some solutions that you've maybe found.
Yeah, I mean, I'm in Montpelier in a very clay spot myself. So, and I do have a rain garden. It does not infiltrate very much. It acts more like a pond, but I put a sand-based soil media in it. Actually, I have two, but one is pretty big, and it captures a lot of our landscape. There's a little fraction of the bottom of the driveway that doesn't cooperate from a topography standpoint. So I know you can do this on clay, but I would say, given what you're describing with the high groundwater table, which is also an issue um, for chloride pollution. So, like the state of Maine has really big challenges with infiltration related to salts. Um, Wide and flat is better than narrow and deep, but that immediately speaks to how much land area do you actually have. I think it's more expensive, but some of the pervious pavers and pavement systems, like for patios in particular, and parking spaces, if not actual driving lanes, can be really helpful because they're designed, and you can even have an impermeable membrane at the bottom of them to not let the water intersect with the groundwater table. But they are designed to have a reservoir underneath them. It's not just like, you probably know this, Shane, but it's not just like a series of paver bricks and the water goes in between. There's also a subsurface layer in a layer cake model of different sizes of stone and gravel that has the void space to hold the water. So it goes through, but then it's also sort of trapped subsurface. I think larger cisterns can be an option. I do also think green roofs, I didn't talk about very much. I showed some images. Green roofs over things like carports, potentially rooftops that are able to take the weight of that material can be a good solution. A lot of it is kind of a site by site analysis. But that's actually part of the bigger question I have about like cumulatively moving downstream. If you have, a whole neighborhood that really doesn't have the space, could they carve off some piece of shared land or collectively be involved in a public project that's just a little bit downstream, and maybe that can be bigger and offset some of the work on their own sites. But I do know of some pretty successful and very dense urban areas that have clay soils and have been able to install GSI.
Cool, cool. Well, kind of what you were alluding to there, the neighborhood size, kind of brings me to my next question, because we're dealing with a lot of 3 acre sites and residential sites. Um, and so as we're working through bringing these neighborhoods and developments up to compliance, with our MS4 requirements of flow and phosphorus reductions, I would love to use some more efficient BMPs, like the bioretention cells that you were diagramming. Those three. I went to the in-person tour of the subsurface sand filter and was really inspired by those. But I wonder if and maybe it's just waiting till the next VSSM comes out. But if you've come into any scenarios or have any tips for, if we are trying to, go for a more effective phosphorus removal tool, but maybe it costs more. But on the regulatory side, are we actually going to get the phosphorus credits or whatever, that it's actually producing and removing from, versus are we just going to get the standard
Yeah,
phosphorus removal for a sand filter kind of thing?
I have done a round of suggested edits on the draft of the Vermont State Stormwater Management Manual that you're referring to. And I do see it moving in the direction of where it already was starting to go since the 2003 manual of use green infrastructure first as a first and foremost strategy. I'd be happy to talk to you about some of the specifics as well with the 3 acre permit that I haven't personally had to deal with from like your side of it as a practitioner, or a representative of a municipality. But I do think that sometimes people need to just have a creative perspective about where they can find space on a site. And I think there's some really amazing examples, in particular around the Twin Cities in Minnesota, of shared achievement of policy among different landowners that have turned into these just incredible pond park systems and sort of MOUs between landowners that have enabled multiple sites' water to be managed in the same place, slightly off-site, that I think could potentially work in a lot of these 3-acre permit situations. So as far as I'm not someone who gets to read through the permits and assign credit, but I know that there's a lot of enthusiasm around these testing requirements, and I would feel much better about anything implemented that use soil media without testing requirements. So I can kind of go back to here to make sure people saw the link. I know that at the state, they understand where these requirements are derived from, and so here we go. I think it makes a lot of sense to design systems that preemptively use them even before the next stormwater manual comes out.
Mm-hmm. Cool. Well, thank you. Appreciate it.
Yeah. Thanks for your questions. This is a quiet group. I talked really fast and went over a lot of different studies. I am very interested in going forward and collaborating on this bigger question of like the additive and cumulative nature of GSI and scaling it to the point where we can take some of the pressure off the floodplains. And no one asked me this, but I don't think we're going to be able to use GSI so much in the upper watershed that we will never have problems in our floodplains and in our many downtowns that are built in these downstream settings. But I also think we can significantly reduce how much water in a 10-year storm, say, or a 25-year storm, instead of these 100-plus-year storm events that we've been having, that we should not be letting these little storms cause combined sewer overflows and damage our rivers and shorelines and cause erosion and so forth. Like there's a lot we could do that we're not doing.
Stephanie, we're close to time, but I'll jump in with one quick question if you'd take one more.
Sure.
I'm wondering if you and I have talked about this before. I'm wondering if you have any thoughts on using some of these principles on our extensive road network up in the uplands. So much of our development in the uplands is pretty distributed and rural, but the road networks channel a lot of stormwater during events. And the municipal roads general permit has sort of pushed us into stone lining ditches and things like that, but not much in the way of green stormwater design.
Yeah, I mean, a little bit this speaks to the survey of the more rural towns and also some other work related to even the salt management practices and road salt. I didn't talk about today, but we have some other projects like mapping salt storage facilities around Vermont. A lot of the road crews sort of lack the space to achieve the storage, and so they're maximizing conveyance. And it's not just like the individual road crews, it's like the sort of design philosophy of our rural communities. So the stone lined ditches and the extremely wide ones that many of these towns have put in are just to keep it's the opposite of the GSI idea of soaking into the land and sponging it up. And there are places we could think of as like sweet spots where we actually have sandier soils, for example, where there is more opportunity to infiltrate that I think should really be considered from a mapping standpoint. I also, would like to see sort of more thinking from like not just the road design itself, and you're the pro at this, Beverly, so I don't want to, you know more than I do about the back road systems, but I think using the principles in getting us out of the right of way and thinking about where we can sort of shunt water off into other places, and maybe there's buyouts for farm and forestry land uses, or even some of the large residential property owners, where you can direct some of the road runoff to a cool pond in their front yard, and they get, some compensation for giving up that land area. Maybe they don't need to mow it anymore or something, but that we're kind of thinking collectively and creatively about the narrowness of these linear right-of-way systems being so limiting on what can be done. So yeah, that's, I think, thinking big and outside of arbitrary boundaries is probably a good approach. Thank you.
Thank you, Stephanie. That will be the end of our Zoom today. Thank you everyone for joining, and I'm going to drop a link into the chat if you're not on our mailing list so you can hear about our upcoming spring seminar. We're working on developing that right now, but we'll hope you will stay tuned for that and come join us in the spring.
Thank you, Stephanie.